Hello everyone, welcome back to our class. Let's continuously study Chapter 11, Mass Transfer. Heat and mass transfer analogy. Accordingly, heat and mass transfer relations for particular geometry are interchangeable. So we obtained a relationship is show the number is a function x style, Reynolds style, and Smith style is a function x style and Reynolds style, Smith power nth. Similarly, we obtained the relationship heat transfer. Nusselt number is a function x style, Reynolds plant also equals similar to f function x style, Reynolds style, plant power nth. So we can do some change, obtain Nusselt number over plant number power nth equals show the number over Smith number power nth is similar to HL over lambda divide plant number power nth. Also equals HML over DAB divide Smith number power nth. We can do some comparison, obtain this equation. Certainly is similar. It's not exactly equals. Finally, we obtained heat transfer coefficient divide mass transfer coefficient equals lambda over DAB times Lewis number power nth equals rho Cp Lewis power 1 minus n. Here is some comparison. In this section, we will study very important analogy. It is Reynolds analogy. When dp power style, dp style divide dx style equals 0 and plant number equals Smith number is similar to 1, we can find that the equations of mass, heat transfer, and boundary layer are similar. In this case, is similar. Therefore, they should have similar form of solution. We can do the comparison. We can do some comparison. From the heat transfer and mass transfer comparison, we easily obtain Cf times Reynolds number divided 2 equals Nusselt number equals shoved number. Define the standard number as follows. Standard number equals H over rho VCP equals Nusselt number divided Reynolds number times plant number. We can call it standard number. Also define the mass transfer standard number. STM means mass transfer standard number equals HM over V also equals shoved number divide Reynolds number times Smith number. This equation and this equation is similar. It's very similar. Here is standard number, mass standard number is similar. Okay, it can be gotten finally. The friction coefficient divide 2 equals standard number and standard number mass is similar, just similar to the friction coefficient, high friction coefficient. So when both the plant number and the Smith number are approximately 1, similar to 1, plant number, Smith number is similar to 1, we have the same standard number as mass transfer standard number. And both are equal to half of the friction coefficient. This is the famous Reynolds analogy. If you make some modification, you get a broader Reynolds number comparison for a wider Planck number and a wider Schmidt number. So half friction coefficient equals standard number Planck power 2/3. And Cf per second, Cf divided 2 equals standard number m times Schmidt number power 2/3. This equation is very similar. Just a look in the the formation is similar. The range also is similar. Okay, we just discussed analogy. It's a famous analogy. So just to say, in some conditions, the heat transfer and mass transfer is similar. We can use the Reynolds analogy to calculate heat transfer coefficient and mass transfer coefficient. Sometimes when we understand H, we can calculate Hm. If we understand Hm, we can calculate the H heat transfer coefficient. Okay, as an example, in this section, we will discuss evaporative cooling. An important application of the heat and mass transfer analogy is evaporative cooling, which occurs when a gas flows over a liquid surface. The evaporation of liquid molecules require latent heat, which comes from internal energy of the liquid. So the temperature of liquid will decrease. For example, in this case, in this picture, according to the energy balance, certainly the convection heat transfer equals evaporation and add some heat transfer into the liquid. If the radiation is 0, we obtain this equation. Only for the energy balance law, we easily obtain this equation. Okay, amount Q evaporation can be approximated as the product of evaporation mass flux density and latent heat of evaporation. Very easy. Q evaporation equals NaHFG. HFG is the latent heat of the liquid. In the absence of other forms of heating, above equation can be simplified as a balance between convective heat and evaporative heat loss. Thus, heat H temperature difference is H T infinite minus Ts times heat transfer coefficient H equals Hm times HFG times the density difference. One density is at Ts, one density is T infinite. So we obtain this equation from the analogy of Reynolds analogy. We easily obtain this equation. Here, the steam density at the surface is relative to the saturation state corresponding to the surface temperature. So surface temperature, we should understand the temperature in the surface. And the cooling effect can be expressed as the temperature difference T infinite minus Ts equals HFG times Hm over H times the density difference. Use the heat and mass transfer analogies given about, for example, Reynolds analogy, H over HM equals K over DAB times Lewis number power nth. Finally equals rho Cp LE Lewis number power 1 minus n. We obtained this equation. So H over HM, most of the case we use this equation. Sometimes we understand H to calculate HM. Okay, the vapor density is written by the ideal gas law. So the cooling effect can be further expressed as by this equation. Cooling effect, just the temperature difference. T infinite minus Ts equals MAHFG over R rho Cp Lewis power 2 over 3. LE is Lewis number. So PA divided Ts. PA means the saturation pressure, partial pressure. PA infinite means pressure in very long distance, the pressure. Divide T infinite. To be more accurate, the physical property parameters of gas component B should be calculated using the mean temperature of the thermal boundary layer. So sometimes we calculate the temperature is average temperature is T infinite plus Ts together, divide 2. Above results are accurate for evaporation of water in air. Here is for cooling, evaporative cooling effect. Thank you.